I'll discuss electrochemistry topic today. Electrochemistry mainly comprising 4 parts. One is galvanic cell and Nernst equation. Second one, the conductances. Third one, batteries. And fourth one, application of these Nernst equation. And Faraday's laws are there. One by one, we'll discuss based on the textbook. In electrochemistry, there are certain cells named as galvanic cells and Daniell cells. Look at one by one. We'll discuss how they are constructed. For example, take zinc sulfate solution. This is aqueous solution. And if you place zinc rod in it, then there is no chemical action. No chemical reaction. But potential difference is there. Why? Because zinc is in metallic state, Zn+2 in aqueous state. So in thermodynamics, if physical state changes, automatically the potential difference arises. So zinc rod and Zn+2 ions differ in their potential, but that potential does not lead to any chemical reaction. This is one. Look at one more example. Copper rod is placed in zinc sulfate solution. This is zinc sulfate solution. And this is copper rod. Here also, the potential difference arises. Copper rod is different from zinc. Abnormal potential difference is there, but no chemical reaction takes place. Here also, no reaction. Look at the third example. This is a copper sulfate solution, aqueous solution. This is zinc rod. Here also potential difference is there. Zinc rod, when placed in copper sulfate solution, potential difference takes place. But here, reaction takes place. Chemical reaction takes place. Here, chemical reactions are absent. Likewise, so many chemical phenomena were observed. Based on that, some electrode potentials likewise were discussed. So look at these three differences. Zinc, in zinc sulfate, no action. Copper, in zinc sulfate, no action. But zinc rod in copper sulfate has a chemical reaction. What is that chemical reaction? Zinc rod dissolves completely by losing electrons. So it will be like this. Zinc rod reacts with a Cu+2 ion present in the copper sulfate, and zinc changes to Zn+2 and copper +2 changes to copper. This is the reaction. This is a redox reaction. That means zinc loses electrons and acts as a reducing agent, because metals always act as a reducing agent. Cu+2 takes electron and acts as oxidizing agent. So this acts as a reductant and this acts as oxidant. And finally, what happens? Copper sulfate aqueous is blue. The blue color of the solution disappears. Why? Because there is no Cu+2 in the solution. Instead, it changes to Cu. And zinc rod vanishes out. That means no visibility of zinc rod after a certain period. Slowly, zinc rod dissolves and finally changes into copper, that is a zinc ion. The final is copper sulfate is changed into zinc sulfate and Cu+2 changes into Cu. Cu plus 2 changes into Cu. This is a chemical reaction. That means potential difference between these two leads to the chemical action. So these are the simple 3 experiments. Now, look at example 4. Zinc rod is placed in its salt solution. This is zinc rod. This is zinc sulfate solution. Take 1 molar for our convenience at 25 degrees centigrade. No reaction, just I told you. No. Copper sulfate solution. Copper sulfate solution of 1 molar at 25 degrees. That means at room temperature. And here, copper rod. No chemical reaction. No chemical reaction. But when this zinc rod is connected to this copper rod by using an electrical bulb here, zinc rod is now in contact with the copper rod. That means both are metals. So what happens now? The electrons move in this direction and it comes here. So here the electrons mobility takes place in this direction. These electrons move into the electrical bulb and bulb glows. And finally the electrons will come here. So in this, zinc changes to Zn plus 2 electrons. These electrons are going in this direction. And this copper rod takes electrons. And here what happens? Cu plus 2 changes to copper sulfate, changes to Cu metal. And this reaction takes place only few seconds. Why? Because these electrons will go here and these electrons are gained by the Cu plus 2. And the reaction stops. Why? Because in everywhere, to complete the movement of current, the circuit should be closed. Here, the electrons are moving in this direction. Electrons are moving in this direction. And they are taken by this copper ion present in the solution. And reaction stops. If the circle is completed, then this bulb continues to glow. But the circle is stopped. Why? Because here, what happens? The solution gets zinc ions. Because zinc rod dissolves into zinc. And here it is positive charge is established. Positive charge in the solution. Here it is Cu plus 2 deposits here. Negative charge is established here. The solution gets positive charge. This solution gets negative charge. If this negative charge is removed and positive charge is removed, then automatically, if the positive charge is removed, zinc ion comes like this. If negative charge is removed, then copper ion goes up like this. Therefore, the continuity of reaction takes place. So this solution becomes positive charge. This solution becomes negative charge. Now, if these two charges are nullified, then the reaction is completed. Then the bulb continues to glow. So look at this. Here, what the substance used here, a salt bridge is used. Negative charge will be moving in this direction. Positive charge will be moving in this direction. Negative charge moves in this direction. Positive charge, because salt bridge is nullifying the charges accumulated in the compartment and this compartment. Here oxidation takes place. Therefore, this is called anode compartment. Here reduction takes place. This is called cathode. This anode is represented with negative plate. Negative plate. Why? Because the surplus electrons are going like this. But the solution has a positive charge. Don't get confused there. Negative plate. And here it is. Solution has a negative charge, but it takes electrons, hence it is positive plate. So anode is represented with a negative plate because zinc gets negative charge due to the surplus electron. Cathode is positive charge due to gain of electrons. To gain electrons, definitely it should have some positive charge. But solutions are in opposite. To nullify these charges in the solution, salt bridge is there. Now the current continues to glow. So here the bulb continues to glow. This is a simple battery. This is a simple battery called, this battery is called Daniel cell. In this chemical reaction, chemical changes are causing electrical energy. Chemical reaction causes electrical energy. Such type of cells are called voltaic cells or galvanic cells. So, or you may call it as voltaic cells, or another name, galvanic cell. Salt bridge has salts like ammonium chloride, ammonium nitrate, or potassium nitrate like this. All salts are not used. Why? Because whatever speed of ammonium ion moves in one direction, the same speed of nitrate ion should be there. Then only the movement of oppositely charged ions at same speed, then only they will be able to nullify the charges. Therefore, all salts are not used in salt bridge. The salts having the same transport number. Transport number means the migration speed of the both cations and anions is same. So all salts cannot be used. Ammonium nitrate can be used, potassium nitrate can be used. Function of this salt bridge is to neutralize charges established in solution. We have seen two half cells, zinc rod placed in zinc sulfate solution, copper rod placed in copper sulfate solution. And these are called electrodes. The zinc electrode, copper electrode. Generally, electrode means which allows electrons through it. Here, electrodes are based on the electrode potentials. That means they have certain potentials. I told you, when zinc rod placed in zinc sulfate solution, there is a potential difference. Copper rod placed in copper sulfate solution, there is a potential difference. Zinc rod in its salt solution, copper rod in its salt solution, two electrodes do not have same electrode potentials because the nature of the metal changes. Hence, zinc electrode has one potential, copper electrode has another potential. What is its potential? To tendency to release electron or sometimes tendency to gain electrons. So based on this, some potentials should be discussed here. Electrode potentials, EMF likewise. So these two terms we come across. Electrode potentials or EMF. This electrode potential, this term is applicable to half cells only. Half cells only, that means single electrodes. What are the single electrodes? I have given the example. Zinc rod in zinc sulfate solution, likewise. Another example, copper rod in copper sulfate solution. This is another electrode. So these are called electrodes. Electrode means it may give electron or it may take electron based on that. So these are called single electrodes. You may get doubt, sir, always the single electrodes are metal in its metal salts. No need to. Electrodes may be metal electrodes or non-metal electrodes. One more example. Hydrogen into H+. This is also electrode. That means hydrogen gas is passed into Cl solution. One more example. Cl2 in Cl+ or Cl- depending upon the solution. When chlorine gas is passed into HCl, when chlorine gas is passed into Cl, Cl-. Therefore, these are all electrodes. These are called metal electrodes. These are called non-metal electrodes. Electrode potentials may be positive or negative. And to define these electrode potentials, we consider a particular standard hydrogen electrode potential. I'll tell you later. Right? Measured in standard state. So they are called SRP or SOP. SRP standard reduction potential. SOP standard oxidation potential. SRP is explained in terms of IUPAC. According to IUPAC, every country or everywhere SRPs are studied. That means these SRPs and SOPs are applied for half cells, for single electrodes, maybe metal electrode, maybe non-metal electrode. SOP can be obtained. To convert SOP into SRP and SRP into SOP, we have to just change the convention, that is sign. For example, if SRP is minus X, SOP is plus X. If SOP is plus X, SRP is minus X. When 25 degrees centigrade and 1 molar is taken, the reduction potential is measured in the laboratory with the help of a reference electrode, then it is called SRP. What is a reference electrode? Standard hydrogen electrode. EMF. This is called electromotive force. What is this electromotive force? Applicable to full cell. Full cells, nothing but voltaic cells. Voltaic cells are galvanic cells, are Daniel cells, are batteries. The full cell EMF. This is so it is applicable to full cells, right? Next, for example, look at this. This is zinc rod. This is zinc sulfate solution. I told you in. This is copper rod. This is copper sulfate solution of 1 molar. This is also 1 molar at 25 degrees centigrade. And here, voltmeter fixed and it is connected. And to complete the circuit, a salt bridge is placed. Here it is, salt bridge. No. This is a aqueous solution here also. This is anode. Since it loses electrons, this is cathode. Since it gains electron, at anode, oxidation takes place. Therefore, zinc rod changes into Zn plus 2 electrons. Reduction takes place here. Reduction means Cu plus 2. Copper ion present here, deposits here, plus takes electrons to form copper. So this is oxidation, hence it is anode. This is cathode. This anode is represented with the negative plate. Cathode is represented with the positive plate. EMF is nothing but the sum of potentials. What potential it has? Oxidation potential, because it loses electrons. What potential it has? Reduction potential, because it gains electrons. Therefore, the EMF is equal to, EMF of full cell is equal to oxidation potential of anode plus reduction potential of cathode. At what conditions? At standard conditions. Because our textbook is based on the standard condition. At 25 degrees centigrade, because in a textbook, if you don't write the standard condition, from book to book, the values vary. Therefore, every textbook refers only at standard conditions, not at ordinary conditions. We will calculate at ordinary conditions. So whatever the values that are given in the textbook, standard values, 25 degrees and 1 molar. So oxidation potential, therefore this may be referred as SOP. Why I have written SOP? Standard oxidation potential. Why standard? At 25 degrees and 1 molar. And this is SRP. SOP of anode, negative plate, SRP of positive plate. This is EMF. Or second one, it may be changed as EMF is equal to, this is SRP of cathode minus SRP of anode. Right or wrong? Why? Because SRP of cathode. This is anode. Anode SOP is changed into SRP. SOPs and SRPs are changed by conversion into signs. If plus is there, minus can be written. SOP has plus sign. So whenever it changes into SRP, it comes minus. So this is another standard formula. This is according to a UPSC. This may be written as SRP of RHS, right hand side electrode. Right hand side electrode minus SRP of LHS, left hand side electrode. In left hand side, we have written anode. In right hand side, we have written cathode. So this is another formula. Or you may write like this. SOP of, this is anode, minus SOP of cathode. SOP, it doesn't change. This is changed. SRP changes into SOP. Plus changes into minus. So these three formulas are used, but this is widely used. These electrode potentials at standard conditions are measured with the help of a reference electrode called standard hydrogen electrode. This is simply named as SHE, or normal hydrogen electrode. It is also named as normal hydrogen electrode. It is also known as NHE. Both are right. Here, the temperature should be 25 degrees centigrade. In states of matter, the standard temperature means 0 degrees centigrade. Here, standard means in thermodynamics and electrochemistry, 25 degrees. Room temperature is the standard temperature. Standard hydrogen electrode is constructed like this. HCl is taken. Here it is HCl of how much molar? Standard condition is 1 molar. At what temperature? At 25 degrees centigrade. And at what pressure? On atmospheric pressure. Now HCl is present. In this, the jar will be like this. Hydrogen is sent in. Here hydrogen gas is present. This hydrogen is at what atmosphere it is sent? 1 atmosphere. This is hydrogen electrode. How it works, I'll tell you. Hydrogen gas is pumped into this solution at 1 molar HCl. But it cannot be passed straight away because electrons should move from one place to other place in the electrodes. One electrode loses electrons. Another electrode gains electrons. The electrons do not move in space. They move along with a wire or rod. Hence, it is a wire is placed here. This is called platinum wire. Platinum wire. So, electrons should move from one place to other place. For this movement, a platinum wire is placed. And here, platinum sheet is there. This is the construction of standard hydrogen. If this acts as anode, tell me. Anode means literally loss of electron. Loss of electron. Which loses electrons? Hydrogen gas loses electrons. This hydrogen gas changes into H+. And like this. So what is happening there? This hydrogen gas is changed into hydrogen ion. If hydrogen atom changes into hydrogen ion, loss of electron. Now, that last electron is coming from this direction. So whenever hydrogen gas is coming in, it changes into H+. And as a result, electrons are deposited here. These electrons move in the upward direction and goes away. Hence, it acts as anode. If it acts as cathode, the H+ ion solution is here that takes electrons from the outer area. That means electrons will come in and these electrons will be absorbed by H+, and it takes like this. This is aqueous solutions. So this acts as a cathode. So standard hydrogen electrode, the electrode potentials of C, electrode potentials of C means standard hydrogen electrode is taken as 0. Taken as 0. Based on this, remaining electrode potentials can be measured. For example, if I connect this piece of chalk here, if piece of chalk loses electrons here, that means if piece of chalk loses electrons and this hydrogen electrode gains, this piece of chalk acts as anode. This hydrogen electrode gains, hence it acts as cathode. Take one more example. If I place some another electrode here, if this electrode loses electrons, it serves as anode. This electrode serves as cathode. Electrodes, two types. Metal electrodes, non-metal electrodes. Metal electrodes means metal rod in its salt solution. Non-metal electrodes means non-metals in its salt solution. So very clear. Now look at one by one. Metal electrodes. Examples. Zinc rod in zinc salt solution. It may be zinc sulfate, anything that is soluble. Maybe zinc sulfate, maybe zinc nitrate, likewise. So this is a metal electrode. Now look at this. Zinc to Zn+2. Loss of electrons. So that potential is called oxidation. Zn+2 Zn. Gain of electrons. That is called reduction. So two ways we can write. Look at one way. Zinc changes to Zn+2 plus 2 electrons. This is a SOP, standard oxidation potential. If concentration is taken as 1 molar, temperature 25 degrees centigrade. Second one, Zn plus 2 electrons changes to Zn. This is SRP. Why it is SRP? This process is reduction. At what conditions it is taken? At standard conditions. So it is SRP. If SOP is minus X, this is in terms of volts. Electrode potentials are measured in volts, right? This SRP is plus X volts. Likewise, we have to write. This is called metal electrodes. And this is simply represented like this. These SOPs are represented like this. So in textbooks and in the questions, it will be given like this. Zinc bar, Zn+2. What is this flash indicates? Zinc rod placed in zinc salt solution. There is a phase difference. Phase means this is in metallic form, this is in aqueous form. Likewise, this can be written as Zn+2 bar Zn. Based on this representation, you have to understand it is a reduction or oxidation. Always we write from left to right side, isn't it? So think from left to right side. From Zn+2 to Zn, +2 to Zn, it is nothing but gain of electrons. So it is reduction. Zinc to Zn+2, loss of electrons. Therefore, it is oxidation. Therefore, this is simply SOP representation and this is simply SRP representation. So if this value is given, that means a reduction potential is given. If this value is given, oxidation potential is given. So this is one example. Another example, Cu plus 2 electrons changes to Cu. This potential is reduction, so named as SRP. So simply electrode is represented as Cu plus 2 bar Cu. If SRP is, that is positive. Now, Cu changes to Cu plus 2 electrons. This is SOP. Why SOP? Oxidation potential at the standard condition, 1 molar, 25 degrees. Then this will be negative. This is represented as Cu bar, Cu plus 2. Non-metal electrodes. Non-metals means chlorine, bromine, like this. In non-metal electrodes, look at this example. Hydrogen changes to H++ electron. Here, you have to balance like this. This is a gaseous substance. This is aqueous solution of how much? 1 molar. At what temperature? 25 degrees centigrade. This is common. Now tell me, this process is oxidation. So it is called SOP. And it is represented as H2 bar, H+. And here a platinum rod is written. Why platinum rod? I told you in the hydrogen electrode. This is a gas. That gas doesn't allow electron into or out. So it needs some wire. That wire is platinum. Hence it is written like this. Next, look at this, another example. H plus electron changes to half H2. And this is 1 molar. At what temperature? 25 degrees centigrade. So this is referred as SRP. So whenever it is SRP, the hydrogen electrode must be written as H plus bar H2 flat. This is a solution. In solution, electron moves, but in gases, electrons do not move. Hence, the platinum rod is printed here. Chlorine electrode. Look at this. Cl2 plus 2 electrons to form 2Cl minus. Gain of electrons. So this value SRP, standard reduction potential. In such a case, its concentration 1 molar, temperature 25 degrees centigrade. Or you may get out like this. Half Cl2 plus electron changes to Cl minus SRP. Here SRP is plus X. Here also plus X in terms of volts. Here you get doubt. Every student get doubt. Sir, electrons, 2 electrons. Here 1 electron. In equilibrium, K value gets cancelled, not based on the electrons. So do not take these electrons. If electron changes, SRP changes, likewise, it never happens. So whatever the number, which is balanced, SRP is X volts. This is also balanced. SRP is X volts. You should not make this likewise X by 2 because electrons are halved. Therefore, electrode potentials halved. That should not be happen. So if total reaction is balanced, that is enough for us. So this is SRP. Therefore, electrode is represented as how? This electrode is represented as Cl2 bar, Cl minus. This is a metal or non-metal? Non-metal. Therefore, platinum. Or right, next step. R. Cl minus changes to half Cl2 plus electrons. What is this? Cl minus loses electrons. Therefore, this is oxidation. Therefore, this value is SOP. Its value is taken as minus X volts. Because SRP is plus X volts, SOP is minus X volts. Or you may represent like this. 2Cl minus gives Cl2 plus 2 electrons. Here also, SOP is minus X volts only. Based on the electrons, SRP and SOP do not change. And how do you write for this? This SOP is written as Cl minus 2 Cl2 platinum. Look at this. Minus to 0. Minus to 0. Loss of electrons. Loss of electron is nothing but oxidation. Here, 0 to minus. Gain of electron, nothing but reduction. So always think from left to right side writing. Based on that, you will get the values. So if you are able to differentiate these things, it is very easy to understand in this equation. In the next class, I'll tell you.